I'm gonna also email. Yes, go ahead, David.
Is the group individual? Can it be a group work?
That's an excellent question, and I would like to know what you guys think. So first, in the class over here, who like to have a group project? Raise your hand. No one. Whoever like, well, you did this, right? You didn't care. And who like to have individual projects? Raise your hand. I get two. So 2.5 against half. So how about this? Actually, online it would be a mess if I ask you to speak up your mind right now. But I'm gonna send an email and saying what is your preference, okay? And also in that email, I'm gonna ask you to reply to like 2 questions. How is the course going so far? What do you think we should change to make the course more fun, rather than wait till the end to tell me, well, we should have done this and that. So now with the project, I'm gonna listen to what you guys decide. If the majority decide to do a group project, we'll do that. If the majority said no, we want individual, we will do this. Okay, and actually we can also have the option, people can opt out. Like although there's a group project, people could say, no, I'm really comfortable doing it by myself. So in the age of COVID-19 and the fact that we don't hang around that much outside together, it's hard to do a group project. So that is, but it is really fun to work together. But I'm gonna to listen to the majority. So whatever the majority decide, we will allow this to happen.
Thank you, sir.
All right. So last time we basically said they try to make the material of the collector very absorptive and does not emit that much. And they try to put cover on the glass so that they wouldn't allow heat transfer to escape. And as a result, the Q absorbed would be big and the Q loss hopefully would be small. And as a result, the difference between them, which is Q useful, which will be m dot CB delta T for the water, will be big. So he will have, if you divide this Q useful over the incident radiation time the area, that is the efficiency of the collector. If you are successful in lowering losses and increasing the absorptivity, you will end up with higher efficiency, okay? So that Q loss, when you think about it, is Q loss by heat transfer. Huh? The tank is losing heat to the outside because the water inside and the plate inside is pretty hot. So the moment there is temperature difference, heat transfer would follow. So in the summer, your house is so cold and the outside is very hot, heat transfer will come from the hot outside into your house. And that's why you have to make the air conditioning work to pump back that heat that seeped through the wall. Okay, so now this time, this is very hot. My sister live in Alberta, Canada. And when we had minus, that like few days of like we had what 0 almost or something. How low did it get? I forgot. -7. I called her and I said, like, how cold are you there? Like, if we are here -7, what you guys are doing? And she said it's okay. It's just that you cannot walk that off like much outside. Like if you walk outside for like 5 minutes or something, then it really hurts. Like your skin will really hurt after that. So in there, the house and the outside, huge temperature difference across. So the wall need to be really thick. The insulation need to be really huge. Otherwise, the heat will just really run outside, right? So the Q loss is dependent on that temperature difference. T minus T. T inside minus T outside. Outside T ambient, inside there is actually 2 temperatures. What are the 2 temperatures inside? T water in, T water out. The water come cold and the water leave hot. So the temperature in the middle is a good representation of what is the temperature inside. T average. The only problem with T average is that we don't really know it. Like when you are picking that heater in your calculation, you just know what's your T inlet, but you don't really know yet how hot he will get. So you don't know T outlet yet, and therefore you don't know T average yet. So you will see that in the next page or something. I would basically say let's do it over T inlet instead. But T average is really a much better indication of the temperature of the plate, right? So T minus T multiplied by area time U. What is U? Overall heat transfer coefficient. Okay. So this is to remind you of the heat transfer course that you guys had before. And in that course, in order to calculate the Q, you need temperature difference and you need the resistance between them. And that resistance could be conduction resistance, like wall, and you have temperature difference, and you would say, well, Q is delta T divided by, what was it? T area over L, right? So it's L over Ka. That was the resistance. L over Ka for a wall, right? And for a cylinder, it was ln R2 over R1 divided by 2 by KL. And for a spherical shell, it was like some kind 1 over R minus 1 over R over stuff. But in any case, it's always delta T divided by a resistance. Okay? And so if the mechanism is conduction and then convection and then conduction and then like adding all those resistances together, that would be the total resistance between the two temperature. So wall painting and then the brick and then the insulation layer and then the cover from outside, you add all those resistors together and that will be your total R. You can alternatively call it 1 over UA, where U is the overall heat transfer coefficient. So when you do this, when you say that the Q is delta T over 1 over UA, alternatively you can say Q is AU delta T. So this is nothing but Q is AU delta T. And it should remind you of, this equation should remind you of the heat transfer by convection, which we used to say AH delta T, right? AH delta T. Okay. So now this UL, that overall heat transfer coefficient, have everything inside it. This is just a lumped number. There is a free quiz, not free quiz, free homework problem, sitting on really, based on you that you really understand what this UL is. Okay. So if this is Q loss, and again Q useful is Q absorbed minus Q loss, therefore Q useful is Q absorbed minus Q loss. Okay, so that is Q loss. A collector, U delta T. A U delta T. Now what is Q absorbed? Well, Q absorbed is first Q incident. How much radiation is coming? A multiplied by I. Okay, what is I? The incident radiation. The watt per meter square falling on our collector because of the tilt, because of where the sun is, because how hot the day was. At the end of the day, you get a table that tell you this is how much incident radiation in Tulsa, Oklahoma, during a certain day. And so for the project, we can make it really long and say, well, let's calculate this for every single day of the year. And then you will hit me and you'll hit yourself and you'll hit the course. Or just to prove that you can know the calculation, we can base the whole year just on one day. So this will cut your work, but it just show me that you know to do the calculation. So changing different days to do different level of heating is not going to be a big deal for you. So I'm thinking we should just base it on, say, let's take the whole year as March 21st as a good average between the summer and the winter. And then if you just show that you can calculate this for March 31st, then it wouldn't cost you anything to just let's do it for the rest of the year, right? So in March 31st, sorry, March 15th, 21st, we said, sorry, March 21st. On March 21st, you will be able to figure out how much incident radiation I is falling in Tulsa, Oklahoma. Normal radiation, if you're gonna make the plate tilted well, normal, right? You don't wanna, you are not gonna put it horizontally, right? That's gonna be less radiation. So you can get the incident radiation on a normal plate on March 21st. And that would be your AI. So AI multiplied by the area of the collector, that's how much watt. So watt per meter square multiplied by meter square, you get what? Time tau, that's the sensitivity of the glass plate, glass cover, time alpha. So this tau is a fraction of how much will go through, and then alpha is how much will actually get absorbed. Not everything that goes through the glass will get absorbed by the plate, unless the plate has a 0.999 absorptivity, right? So people actually add those two guys together, tau and alpha, and you can see them in a over here. Tau and alpha are those are typical number, and here is UL, the overall heat transfer loss coefficient, how much you are losing. Okay, so he's saying that if you add more and more cover, rather than one glass cover, you have two glass cover, your loss coefficient drop from 1 to 0.6. Of course, if you don't have any cover, your loss coefficient is 6, because you are just, this is someone in the winter that opened his window. So of course, all the heat transfer will seep through. One cover is 1, and two cover is 0.6. But in the process of reducing UL, look at this. Your tau alpha get less by adding more glass cover. Why? And more layer, how is that hurting? Because of reflectivity, right? Because each layer reflects some of the glass out, some of the radiation out, right? So it does increase with UL, but it go down with it goes down with how much you actually get transmitted and absorbed. Okay, so but there are applications, again, we said last time that people will, it's okay for them to have no cover, huh? Like this, look at this, no cover. How come? So the plate, this is the collecting plate, and the pipe is basically bringing the water through, compared to the one with a cover. Why? Because this is just for heating the house, and the guy doesn't wanna really burn the house or anything. He just, the smallest amount of delta T is good enough for him. He doesn't want the house to be that hot. And that will be very cheap to maintain, and it's not gonna break. There is no glass that will get damaged by hail, right? So people do go to extreme cases, to try to show how good their water heater is. And sometimes it's small things, just like the frame and how easy you can tilt it, because he's sitting on like really hinges. But sometimes it's like more complicated things about how big the alpha is and how small the epsilon is. Look at this, alpha 0.96 and epsilon is 0.08. That's a very good selective material. Absorb but doesn't radiate back. Okay. So, and the weight, of course, the lighter it is, the better, right? So that you don't put that much weight on the roof. And the lifespan of the heater is important, because solar water heater will not cost you electricity during their life. You're just sitting there, taking the sun, heating your water. But how is it fair to compare it with an electric heater that suck electricity from the grid? It's always the price per the levelized cost of production of those things. So levelized cost of water, for example, if you are doing desalination. So you want to see after 30 years, assuming this guy really live, I mean, the warranty is 10 years, so I think we should base it on the warranty. So if the warranty is 10 years, then this guy need to pay back his cost in 10 years. By 10 years, we assume he has no warranty, then he can fail on us. So the electric heater, his energy cost per day time the number of days per year time those 10 years better be cheaper than this guy. Otherwise, he's not competitive. Otherwise, we should go with this guy. Okay, so what I'm saying is for renewable things, you need to figure out how long they will live, and then either you divide their total cost over the number of days and you figure out what's the price per day, or do it the other way. For the non-renewable one, the one that uses electricity or natural gas, you calculate their running cost all the way up to 10 years, and you compare the price of the two at that time. Okay, so it's the total cost over the lifespan of the project, basically. Okay, good. So here is Q useful, and this is just the equation that we just wrote. Okay, and he is over here. We are basically saying that the hotter the water, the less the Q useful would be. You can see that mathematically, if T average is really high, Q useful will be less because the negative sign. And physically, what does this mean? It means that if you want the water to be really, really hot, it will leak like crazy from the tank, from the box, right? So you are not gonna, this thing will not collect that much heat. Okay. So now the efficiency, if we want to calculate the efficiency, we divide this Q useful over what? I, A. So I will cancel with I and A will cancel over here, and this I cancel here, but the I will show up over here. So you will end up with UL and T minus T over I. This is a straight line equation. This is the intercept and this is the slope. Okay, when this is the X variable. The X variable now is T minus T over I. T average minus T ambient over I. That's our X-axis. So if I plot my efficiency against this variable, I should get a straight line. Here is the efficiency, and here is T minus T over I. T average minus T ambient over I. Okay? And back to this equation for Q useful. If T average go really high, if I go all the way to this end, T average gets really, really high until Q useful becomes 0. What that mean? What scenario does this describe? Q useful is 0 and T will be T max. How can I duplicate this scenario in real life? How can I get my water heater go to the maximum temperature he can achieve? Because that is this point. This point when the efficiency is 0 means that T average hit its maximum. And that's why Q useful is 0. And that's why the efficiency is 0. The efficiency is 0 not because there is no incident radiation, is that because you're not getting any Q useful out of it. What is that scenario? Well, if you have 0 efficiency, you will probably have to use something else to supply, right? So you need, of course, if you have a solar system, you need to have a backup. But how strong is the backup? Should we have like a full, natural gas heater standing by for case the solar heater is not working, or should we have like a small electric auxiliary unit that can just like help a little bit? Probably a small heating unit that not designed to work all the time and just supply the difference, right? But back to the question, how do I get this point? How can I get zero efficiency? And that corresponds to maximum T average. When will this happen? This will happen if the inlet water and outlet water are shut down. The water is stuck in here. If you have zero flow rate, what happened to the water in this place? Hot, 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 until what happened? No, it will not pop the pipe. It will get hot enough to the extent that the losses is equal to the incident radiation. It take a certain temperature, you hit this point, and then you basically radiate back everything. This is the temperature that the car seat will reach when you close close the window, and you don't let air in or air out. The air will get as hot as it can and stops. A few years ago, one of the students came back after she graduated, and she said she had this problem with her company make kind of tablet, PC for oil and gas working in the Middle East in the desert, and it gets so hot that the tablet kind of melt almost. She said they melt from how hot it is. Okay. And so she was trying to find a solution to make them not to melt at that high temperature. So why does the tablet get really that hot? Same concept. The tablet need to be, he has energy generated inside, right? All this battery is running through those circuits to make calculation and do things, and he get heated. So now how hot he should get? How hot should this tablet, here's my tablet, how hot he should get? Why does he need to get hot to start with? Because he need to spill away that heat, right? The heat generated inside by the circuits need to be thrown away. Thrown away to what? To T ambient that is really high. In the desert, T ambient is like 120, and the tablet need to go to 100 and whatever so that he can spill the delta T, so that his Q that need to be equal to whatever is generated inside need to be equal to AU delta T, right? So how do you solve this problem? I mean, those Q need to go out. There is no question. Whatever is generated inside need to be thrown away. So how can you do this without having big delta T? What else you got in that poor equation? AU delta T. Yes, excellent. So they actually had fins coming out from they designed some kind of like heat sink that is leaking, like going from the inside to the outside. And they made like heat pipe. If you remember, if you know heat pipe, is a way to basically take the heat from one place to the other by use it in the National Space Station because there's no natural convection. Like if you are in space and this computer is hot, the air does not go up and leave. He sit around. Everything sit in its own thermal bubble. Because why would the heat go up? There's no reason for the heat to go up or down or right or left. Okay. My point behind this is to explain. So this is all has to do with understanding the mechanism of this. So this is basically telling you, you have to give me delta T so that, and a small resistance so I can spill my heat out. Okay. And so when you shut down the inlet and the outlet, this guy will go up enough so that all the incident radiation time the area will be equal to AU delta T. Right? So T average will have to go all the way up. So This point also, it mean this way, but it also mean maybe T ambient is very small. Like in the winter months, huh? It's not that the flow rate is 0 and this thing heated from us so hot. Even with a moderate flow rate, with really big, really small T ambient, you're gonna be over here. So the water will go in the water heater, and the ambient outside is like -5 degrees Fahrenheit. Of course, it cannot be water. It has to be something with antifreeze, right? So anyway, this basically represent a demand on there's huge demand on the system. So it's either T average is very high or T ambient is very low, or I also could be the reason why we are pushing this way. Maybe I is not that big. Maybe we don't have that much incident radiation coming in. So if I is big, we will go this way. But if I is really small, we will go that direction. At the end of the day, the equation is linear, and you'll be able to calculate how much is coming out depending on the x-axis and that curve. And so that curve is basically those two guys, right? The tau alpha and UL. The manufacturer actually, when we see the certificate that they supply, they will give you the tau alpha and the UL. Okay, so now the T average thing. So for design purpose, Tn is more convenient because we know what's Tn. Water coming from the ground. And so, but that's not how the equation was written. So in order to fix our mistake, they add a factor here, Fr. And that factor is called the collector heat removal factor. So now you multiply this Fr and it becomes Fr tau alpha and Fr UL. So in the chart, if the variable is Tn minus T ambient over I rather than T average minus T ambient over I, then the intercept and the slope is Fr tau alpha and Fr UL rather than tau alpha and UL. You get the Fr attached to it. Okay, and that's convenient because now you can immediately find out for any T inlet what would be the efficiency. And once you know the efficiency, well, the efficiency is input multiplied with the efficiency is going to be m dot CB delta T. So you can actually calculate delta T out from that system. Okay. So imagine if we just kept it going with T average, it would be one equation and two unknown. I don't know the T average because I don't know the T outlet, and I will not know the T outlet unless I know the efficiency. So like what, I'm going to be iterating forever. But if you tell me the equation in terms of T inlet, then I immediately find the efficiency and say that the efficiency is going to be multiplied by the incident radiation times the area, going to be m dot CB delta T. Make sense? Yes. Okay. Now a little bit to make it more accurate, we'll tell you, wait a minute, this tau alpha, that transmissivity and absorptivity, what angle is the radiation is hitting the plate? Is the plate is sitting on a 2D tracking system and is always normal? That would be perfect. But if it's not, and the angle is a little bit steep, one can see that if the incident angle, remember theta I, we had an equation for it, which was not in the book, but it was in our notes. So if we know the theta I, and the theta I is 0 or 5, that's okay. But if theta I is 40 degrees or 50, so he's like, the radiation is coming with a huge angle. That probably will make the transmissivity not that great because the reflectivity will pick up some, right? So what do? They fix this tau alpha. So they tell you there is tau alpha normal, okay? And you need to multiply by some kind of correction factor, K. So the incident angle modifier, K tau alpha, that guy will be function of the incident radiation angle, theta I. So if you know the angle, you will be able to calculate the the cosine theta I, and from some kind of equation, or sometimes they give you a curve, you'll be able to calculate K. Okay? And so once you calculate that K, now you have a really accurate equation. So this efficiency, well, you can now calculate it for every hour during spring or March 21st, which is our day of choice for this project. We'll say for this particular day, calculate there's an angle on the plate, or the collector, and from that calculate K, and from that calculate the efficiency. And you can see what's the temperature of the ambient also, and Tn, so you'll be able to calculate the efficiency throughout the day. And then you will figure out when will the solar heating was not enough, and we will have to turn the electric heater. And we'll have to fix the load. So we'll have to say like a household where there's someone always in the house and they need warm water, say 12 hours per day, for example, from 7 to 7, they just need warm water. And we'll fix the flow rate so that everyone is calculating a fixed flow rate. Like they are always either taking a shower, washing the plates, washing the clothes with hot water, taking hot tub, whatever. They always need hot water throughout the day. Okay. Very good. So now we have a solid equation for the solar heater. Okay, and that tau alpha and UL and FR is supplier responsibility. And actually, most of the time, the supplier or the manufacturer, the original equipment manufacturer, OEM, will not make that number themselves. They will have to give it to third party testing it for them. Another place they will give them the collector and they give them a certificate. Well, here's your tau alpha, and here is your FR, and here's your UL. Okay, and so from those numbers you get a chart like you get see the. Also, this is something important to realize, that every time you measure something, it's never exactly on the curve. I mean, the theory is something, but in real life, there's like real-time effect. Maybe there's a cloud that day sitting on. Maybe the plate has like a little bit of like smudge over here, which when the radiation was in particular angle, things will went a little bit up. There are all those reasons why things are. But we basically send the curve through all of them, and that will be our best fit. Okay, and will be a good enough for us. Okay. So I explained what is this point, right? This point is maximum temperature you would reach. What is that point? How can I get here the maximum efficiency? How can physically we get the maximum efficiency of the water heater if what happens? I can't hear. No change in temperature. How is that going to happen? Physically, like here's the water heater on top of our building. I want the maximum efficiency. What want you me to do? What do you want me to do to get the maximum efficiency? The water flow rate here is 0. The water flow rate here is, yeah, almost infinity. So if the water come in and leave, it increases its temperature like what? Like a degree or something? It doesn't have a chance to lose, right? To somewhere else. So basically, this is also when Tn equal T ambient. If you don't want the water to get heated that much above T ambient, you don't have that much to worry about, then the efficiency is going to be really high because he's like continuously cooling the plate very quickly, and he doesn't have that much high heat to lose to the ambient, right? So if you have maximum flow rate, you get really high efficiency. If you have small flow rate, you get higher temperature. Very good. So there is a bunch of examples in the book, and they are all about how we can use this equation. Okay. So they sometimes they give you the table, and sometimes they give you the number. So he say, or the chart. He said the tau is 0.9, the alpha is 0.92, and find the collector heat removal factor FR. So, well, the intercept was FR tau alpha. So if the intercept is 0.8, because that's efficiency, so 80%, so 0.8. So if this is 0.8, then FR tau alpha is 0.8, and he just give me tau and alpha, then I can calculate FR from it, right? And that's what he does. He say, well, it's 0.8, and that 0.8 is this guy. And so if this guy is 0.8, that means that, and it's FR tau alpha, that must be my FR. And then he said, calculate UL. Well, the slope, the slope of the curve, how can I calculate the slope? I was just explaining this to my daughter actually this weekend because she is in
Y
this.
by X.
Yeah, delta Y over delta X. The slope is delta Y over delta X, right? So you get this and you divide over this, right? Delta Y over delta X. And so what is that slope? FRUL, and we just calculated FR, so we can get UL out of it. And that slope actually has units, right? And that's why, although FR is dimensionless, just like tau and alpha, just a factor, but UL has a unit, right? And in SI, what's the unit of U? Watt per meter square Kelvin, right? And in English unit, it would be, so see, this unit is wrong. It need to have a degree Fahrenheit attached to it. So the watt is BTU per hour, right? Joule per second. That's what BTU per hour and per meter square. And there need also be degree Fahrenheit. He did it wrong here, but he will do it right in somewhere else. Okay, so BTU per feet square. So BTU per hour. So anyway, he will calculate the slope, and he told himself the slope is FRUL here. So he's saying it's delta over delta, delta E over delta X. And so see, calculating it right this time. BTU per hour feet square degree Fahrenheit. And so he ended up saying, well, then my UL is this much. BTU per hour, that's what? Per meter square degree Fahrenheit. Make sense? So all this is just to make us familiar with the equation and see how this equation is getting plotted. All right? That's basically the point here. And then he's saying, well, the rate at which the collector can deliver useful energy when a radiation incident on the collector per unit is this much. So this is exactly what we're going to do for the project. Because you guys will select a water heater out of, I'll give you a database and you can pick one that's good. And basically you would say how much watt per meter square is falling. Watt per meter square is falling in Tulsa, Oklahoma on my tilted collector. How much this chart or this collector will actually deliver to me? How much is key useful? So in order to calculate this, you need to multiply the radiation times the eta. And how do you get the eta? You need to step here and find the eta. So what is here? Tn, T ambient, and incident radiation to allow you to come up here on this equation and calculate the efficiency. Make sense? Very good. So the rate at which the collector can deliver useful energy when the radiation is this much, the ambient temperature is this much, and the inlet water temperature is this much. That's what we did. Finally, he's just doing this. Yeah, it's the same calculation again. But here, the collector temperature when the flow rate is 0, eta equals 0. That is this point. That is the maximum temperature he will get. And that's when you slow down the flow rate. So the water come in and like stay there forever before it leave. That's the water get like really, really roasted in the water heater, right? And that would be that point. So if you read this point over here and it turned out to be say 0.6, what is that? That's eta equal 0.6. Huh? No, sorry. The efficiency is 0, but the x-axis, which is Tn minus T ambient over F would be say 0.6. That will allow you to get what is Tn. If you find where it will hit, you'll be able to calculate Tn minus T ambient. So that will tell you how high you need to be above T ambient to get that 0 efficiency. Okay, so the collector temperature when the flow rate is 0. Setting eta equal to 0, then this would be equal to this. The losses equal to the absorbed energy. This equal to this. The only unknown is Tn, which is T out, which is T max. Notice how the flow rate when it's really 0, Tn and T out would be almost the same because he's like the flow is not leaving. He's stuck there. So it's 191 degrees Fahrenheit. Questions? So those would be the typical chart that you'll get for different model. Okay, so the supplier, okay, and this solar collector certification and rating. So those are the people who are doing the certification, and this is the supplier who gave them the collector and said, "Can you guys please test my EE21 model?" And so they test at different temperature, clear day, radiation, and out of this, what's really we care about is the intercept and the slope. FR tau alpha and FRUL. See, the intercept is 0.66 and the slope is minus 6.37 watt per meter square. And it's minus, the slope is minus, right? Minus 6.37 watt per meter square degree C or BTU per hour per feet square per degree Fahrenheit. Okay, so he can supply the two number for you, but he can also supply an equation. Okay, and the equation is 6.38 minus 4 b over I minus 0.0297 b squared over I. Okay, wow, that is not linear. This equation is second order. Okay, second order NP. What's P? Ti minus T ambient. So the linear equation is here. That's the intercept and the slope. But if you want to be super accurate, you use this one. And that is not a straight line. That's a little bit curved because it's function of B squared. It's not function of the incident radiation square, but it's function of the T minus T square. And that is your free homework problem question for today. Why? So although it's like really small number, look at this, minus 0.02. But I mean the temperature difference is square. So at really big temperature difference, that guy will make difference. But when the delta T is small, you can forget about it and you'd say, well, I'm happy with this. And notice how it's 0.638, but this one is 0.66. Like you'll be tempted to think that they will make the first order equation by just saying, forget about this, let me cancel this. I'm gonna have you with the first two terms. No, the first order approximation. It's the same data, that is a little bit curved near the end, but they just wanna try to put the best fit curve, the best fit line that goes through all of them anyway. Right? They're saying, just give me, and they do this a lot with heat transfer. Like people would know that the equation is not linear, but they just say, I just want a linear equation to get the equation, to optimize the equation, for example. I just want a linear effect. And so what? It's like 3% error, that's okay, I'm okay. I mean, if even within 10%, we are fine. We are gonna have we are actually going to design our water heater to do twice the load that the house needs. And so we already have a factor of safety built in. So if I'm like 5% off, don't worry about it. So they do this, they approximate the equation for simplicity, especially when the approximation is not that bad. Huh? So now what is the question that you will get a free homework problem if you answer correctly? The question is, why the more accurate form is actually second order in temperature? This analysis here, what was wrong with this analysis that we spent all the first part of the lecture and even a little bit of last week on it? What's wrong with this? This show me that the efficiency is a linear equation of the temperature. Why they are saying no, it's not? So the first person to answer this question correctly and send it to an email to me get one free homework problem. Why this is okay, but actually a more accurate one will have delta temperature square, not delta temperature. Okay. And it's time for our break. So let's take a 15 minutes break and we will come after that. All right, we are back. So guys online, can you still hear me?
Yes.
All right, can you see my screen, right?
Yeah.
Okay. So we said those charts that manufacturer provide, will give us this intercept and the slope. And what is that? Incident angle modifier. That's the K multiplied by alpha and tau, huh? The K that will fix the alpha and tau for different theta. Okay. So he's basically saying, what's the equation for that? He's saying the equation is 1 plus 0.024 s minus 0.0861 s squared. And if you want to use a linear FET, which is easier but less accurate, here it is. Okay. And what's that s? He explained. The s is 1 over cosine theta minus 1, where theta is going between 0 and 60. Denver, question. Well, the question is from Denver. He's saying, like if you are doing Excel or something, the more accurate equation is not that horrible. It's not like shine theta multiplied by te to power log x theta. It's not that hard. It's just like one factor. But there is really benefit to linear equation. Linear equation can be used for optimization very easily. If you have everything in the equation, you can find out the optimum design point very quickly. Any nonlinearity or second order complicate the solution or optimization technique. But you are right. That second order is not that hard. Last year, actually, I gave them a homework to calculate the efficiency with the second order and the first order and compare the two of them. And when you compare the two of them for the range that we examined, there hardly was any difference. So that's why also the linear equation is not that bad, because the error is not that big. You don't notice it. So that's why. And you can tell in how small the digits is, right? So, all right, this is another chart, part of the chart, which also can tell you the manual. It can tell you the pressure drop. So the flow rate, in gallon per minute or milliliter per second going through, come on the expense of pressure drop. A pump need to drive that water through that system. You need to have pressure drop to send the water through a pipe. So we pay pressure drop too. Now, if the city water pressure is enough, then you don't have to worry about it. And what is the city water pressure? What do you guys get at your home? I get 50 psi in the lab downstairs. So we have a pressure gauge, and it's like a big deal for us because our laser system wouldn't run unless the cooling water is coming. And the way he knows that cooling water is coming is by a pressure gauge. So he measures the pressure, and if the pressure is not good enough, he wouldn't run. And then we cannot do any experiment. So that's why I know exactly the pressure of the. So if the city water pressure is big enough to send this, you don't have to worry about it. Okay. This is a reminder of what was cosine theta I, because it's not in our book. Alpha, beta, solar altitude angle, tilt angle, right? Beta, facing from the horizontal beta Ceph, 0. When you go up, it's 90 degrees for vertical wall. And we said, what's the optimum tilt for year-long latitude tilt, right? But we are not doing it in this project for all year long. We will just do the calculation for the spring. So maybe you guys need to tilt it optimally for the spring. Okay. And E is the azimuth angle of the solar collector. And ES is the solar azimuth angle So obviously during the day, AS will be different and alpha will be different because the sun will rise, go up, and then go down. So then you can calculate theta I during the day. And then you calculate K through the day. So theta I and K will change during the day. And what else will change during the day? For the efficiency, the T ambient will change during the day. And that's why the efficiency. So in preparation for the project, maybe we should do those calculations and get rid of them. Let's do this calculation in Tulsa, Oklahoma on the spring 21st. Let's calculate theta I. Let's calculate the K. Let's calculate the efficiency for this guy, the one in our book. I mean, we can choose other ones too, but I mean, we can use this one. Okay. Questions? Okay. So now some people use a lot, not just one, especially if it's a big, like a hotel or like a hospital or something, big facility, you need a lot of them, right? And also the water that's going through doesn't have to be water. It could be an antifreeze, a coolant, just like your car radiator, and then it doesn't really, it heat the water in a heat exchanger. So it goes through a heat exchanger where it mixes with the water, not mix, but it go across a heat exchanger to heat the water that you need to heat, right? You see there is always like an electric heat water just in case the temperature is not good enough. So that will just be like, a coffee maker or something, like just like a small element hooked on the electricity. And when the temperature drop, he basically make sure it's available for him. Okay. So those designs are good, but I'm saying that people would wish for a little bit more. How you can make that even better? What would you wish for? You want to have like some kind of tracking system so that you're always normal to the sun. That would be nice, right? And also you don't want heat transfer between the hot plate and the outside. So maybe instead of air, if we fill it with vacuum, that would be nice. And for the 2D tracking system, even a better, this is specifically for like really for my sister in Canada. Like when the temperature is really cold and you want to use, so I'm not really making a joke here, but where is the largest photovoltaic field in the world? It's in Ontario, Canada. The largest photovoltaic field is Ontario, Canada, because the government there made it tax incentive to make it really profitable for people to actually do this. Okay. In 2009, where is the largest country that put photovoltaic panel? Germany, which had the solar radiation like Alaska, same level of solar radiation. Because their government made decision, we are not going to build any more nuclear reactors. So sometime really cold weather and small radiation will opt for solar energy for political reason or because people are really very green there and they are very sensitive to environment. And so it's not about efficiency. It's not about, it's more about like making a statement that, yes, we want to just run on solar energy. So for such a cold weather, you cannot afford any losses, right? So what did they make? They make this. This is evacuated tube collector. So each one of those tube has vacuum in it. And because the tube, the collector now, the flat plate that is sitting normally under the glass cover now is in inner cylinder that no matter where is the sun, whether it's morning or night, it's always falling on part of the tube. I mean, at noon it's heating the top. In the morning it's heating this side. In the evening it's heating this side. So the tube is always getting heated. Of course, you cannot stack them so close, otherwise they will be in the shadow of each other. So you have to be a little bit far away. And then the question is it fair then to compare what area are we comparing with? I would think it's the total area. This is what he occupy in my roof. And this is basically what I'm gonna calculate the efficiency on. But as you probably think right now, the roof is so big in your house and you are not running out of space. That's not really a big deal. So if it's going to be a little bit bigger but more efficient, you don't mind, right? I mean, you're not going to die if like, wow, it's taking twice the volume of this guy. That's okay. The roof is so big. It's not a big deal. You're not running out of space there, right? But by doing this, they always get normal radiation on their tube. And now each one of those guys, the water actually come here and leave from here. Doesn't go there. So how does the heat go from this place all the way up to that place? This is called, those things, those copper tube, is heat pipe. That's remember the girl that I was telling you about, that she was like trying to cool those tablets in the desert for oil and gas. She was using those heat pipes. So that heat pipe will take the heat from the pipe all the way to the water on top. Okay, so the water will go this manifold and it's being heated by those copper tube. And this is not all pure copper. If we actually look into it, it's a whole heat pump inside, but without any moving parts. What's a heat pump? Heat pump is a compressor, evaporator, and a condenser, and a throttling device that circulate the heat between the low to the high. Okay, so how does this guy do it? How does he take the heat from here to here? Okay, so there is liquid, working fluid, propane, some kind of like exotic fluid. It's not water. That fluid inside will boil, become vapor at this temperature. So this temperature here is hot enough to make him become vapor. And if he is a vapor, he will go all the way. I mean, he can travel, especially that this place will have vacuum. I'm going to tell you why now in a minute. But the vapor will travel from that place that he's boiling from to the place where they don't have vapor and vacuum is there. When he go there, he will find the water that's going in the manifold. He will condense, turn into a liquid. And what's the difference in the density between liquid and vapor usually? It's around 1,000, right? The difference between the density of liquid and water is 1,000. So the difference in specific volume would be 1/1,000. The vapor takes 1,000 times more the volume of liquid water or liquid fluid or whatever the fluid we are dealing with. So what I'm trying to say is that the vapor, when he condenses, his volume shrink, leaving vacuum behind him. That will pull more vapor. Now the question is, how does this liquid that just condensed go down over here? And it's not just gravity. I mean, gravity does help, but it's also, look at this. It's like wicking material. The inside of the tube is covered with wicking material, like a napkin. You know how you put a napkin and the water immediately rise? So there is wicking material that's connecting those things. So when liquid condense and liquid disappear, why the liquid disappear here? Because he boiled, because it's so hot. Liquid is continuously seeping through that wicking material, and gravity could help too, to over here. Where he boil and the vapor find the space empty, he go up here. So those things like connect heat way better than just pure copper. I mean, you could just make the inside copper. This is more effective. How come more effective? Because you are dealing with latent heat, HFG. Anytime you turn vapor to liquid and liquid to vapor, there's huge HFG. You know, in the TS diagram, when you go from HF to HG, 100 on this side, 2,000 on the other side, joule per kilogram. So every kilogram carry with him 2,000 kilojoule. It's a lot of heat that you can just passing by conduction, you will not be able to catch up. Okay, that's why we always have boiling and condensation in all our HVAC machines, all our air conditioning and fridges. Everything of them basically work on what? Let's condense the vapor on one side, let's boil the liquid on the other side. Let's condense the vapor, and between those two places, you dump a lot of joules between your house and between the condenser unit outside. I mean, we could, if conduction was good enough, we could just have big pipes from our house all the way to the roof with a fin, and we are done. Here's yalla, go. Conduction, guys, go, go, go. But no, the latent heat really help. Okay?
Dr. Salam, will that copper pipe be heated too?
So the cover part is inside. Look at this. The cover part, the outside pipe, is in kind of soldered. The cover heat pipe is kind of soldered to the black collector, the black cylindrical collector. Okay, so he's welded into it. So when the black collector get hot, the cover pipe get hot, and the cover pipe move all the heat into the top part that is inside the water. So all those guys are sticking inside the water, and the water come and basically get heated by them. Okay, see how the black collector, it's a cylinder, and the tube is like stuck to it, soldered to it. And this black collector is sitting in a glass tube, and that glass tube is, everything here is under vacuum. So no conduction. No conduction can go from that guy. Everything is just radiation. And if I do a good job selecting the coating, and my emissivity is 0.06 or something, then that guy will get heated and he will not really radiate back. And he's not conducting back because he's sitting in vacuum. So you will just arrest the heat. So this design will allow you really to function even if you are in Alberta, Canada. Doesn't matter how cold you are, this guy will take the radiation and hold to it, and it's not going to go away. Okay. Yes, double the size. But I mean, also look at this. If one of those tubes get broken because of hail, you just replace this tube. You don't replace the whole thing. See, this guy have a crack. You have to place the whole cover. Right? But this one is just like modular, so you can put as many of them as you want, so that temperature get hotter and hotter and hotter. So one after the other after the other. Questions? All right. So I think I'm gonna do the homework just as I told you, so that we can get ready for the project. You know, if we have those calculations and we can calculate the efficiency as function of hour for one place, Tulsa, Oklahoma, during one day, spring 21st, this then will allow us to say, well, if you want this much water, then I need this many collectors. Okay. Very good. So what we did is the calculation of one collector. Now, we need to think about what if we have a lot of them, how do they function? And also, that level of calculation per day, per hour, where is the sun, what's the incident radiation angle, what is the key, what's the efficiency? This is like torture for a big system. If you're designing a big system, you cannot do that for every single hour. So we need another way to calculate, like a rough estimate, how many collectors we need. And they have this method, and it's called the F chart. And we will see how we do this calculation. But first, this neat sketch of how does the system would actually look like. Closed loop for the solar collector. Look at this. This is the pump, right? And the pump is sending the water through, or the fluid, through the collector, relief valve, just in case things get overpressurized. You don't want them to explode. You just want them to go out. And in that heat exchanger, circulate, like heat this, use this to heat the actual water. This is the water that go into the main tank. This is your main tank for the water. Now, this main tank can be used for uh, the over here. You take the water from it and you heat the water supply to the house, but also you can use it for heating over here the building. So not all the water that's being used over here is used for actual water to drink or cook from. You can just use it for heating the place. Okay. When I was in graduate student in Michigan, I was living in the university housing. And so the university housing is basically because it was just across the street from my lab. You know, you cross, you're in bedroom, you cross in the morning, you are in the lab. It was so convenient. And so all those apartments, we were living in like one bedroom apartment, me and my wife. The apartment was had three radiator, one in the bedroom, one in the living room, one in the kitchen. Actually, I don't think there was in the kitchen. There was just one in the living room and one in the bedroom. So those radiator take water from so there is a central heating loop. Water get boiled somewhere and is being sent to all the units in all the apartment. And that hot water just come over here in our radiator, and basically the building get hot. And you don't control the temperature. It's just like central control. You actually don't even turn on and off. You don't know when they will turn it on. So they will tell you, well, when it's cold enough, we will turn the heating. So we had, so that radiator was basically in under the window, and my wife had flowers on them because it's like under the window, it looked nice, you know. And one day we came back and the flowers are almost dead. Everything is dead because they turned on the heaters and they kind of like really dried the plants. And like everything fell down. But what I'm trying to say is that water heating units in radiator is actually pretty common. And if you go to here in North Hall, main hall, all the offices we used before this building was on. I came here 2003, and my office was in main hall. My office was in main hall, second floor. I had a corner office there too. So my office just had water heaters all over the place. Okay, so it's not really. It's actually, when you think about it, it is very quiet compared to air conditioning with air duct. Okay, and a lot of like also very expensive building, not just like old building or university building. Some expensive building use those hydronic water pumps where basically water go and it even go under the kitchen tiles. So your kitchen is like really hot floor, so you can walk, you know, in the winter without wearing any shoes or slippers because the floor is so warm and nice. So water heating in radiator is not out of fashion or anything. It's actually very quiet and common. So notice how the water have an auxiliary, and that's what we will do in the project too. We will just have an electric heater in the tank just to make sure that if the hot solar is not running, this guy will kick in and make sure that the temperature stay hot enough. Okay, very good. So the chart, okay, so this this is done every hour. This is the old method. The new method is going to be next. It's called F chart, but this is like the old style. What's the old style? Let's calculate the efficiency and key useful for every hour of the day. So in order to calculate this for every hour of the day, I need the equation, the efficiency. Okay. So what's it given? The location, latitude, the tilt angle, the day. This is Jan 21st. Delta is. By the way, actually, we didn't really discuss the homework, and we need that homework equation for this project too. So any question about the equation in the homework? We know how to calculate delta from the Julian day, right? Any question about delta from the Julian day? It's the simple equation, huh? Minus the 23.45 sine stuff. The only thing is that this is actually, when you multiply by pi over 180, you turn this into radian. And that's what Excel expects. Right? When in Excel, when you say sine, you need a radian number. And that's why the 330, 360 need to be turned into radian. How do I turn it into radian? I multiply by pi, I divide over 180. Question about delta. You guys got it, right? Yes. So if you did it in MATLAB, that's way better than Excel. Good job. Good job that you did it in MATLAB. Okay. And then the day lengths. I calculate the hour angle at sunrise and sunset. What is it? Cosine minus 1 minus tan delta tan L. Okay, and all this converges to make sure it's radian. But that's the equation we talked about. Cosine minus 1 minus tan delta tan L. That will tell you the length of the day. That's the hour angle. And then I multiply by 2 and I divide over 15 to find out how many hours the day is. Okay, alpha maximum, there is an equation
Yes,
for alpha. Yes.
Dr. Salam, in that previous, for the WS,
Yeah.
the formula for the WS, so what is the function of that A?
What is the function of that? That's cosine minus 1. A cos is cosine minus 1. You know how there is cosine and cosine minus 1? What's cosine minus 1? It's not 1 over cosine.
It's
It's
cos
arc sine.
inverse, right?
So A cosine is arc sine. Arc sine. If you Google arc sine, where is the help? Like if you go help, arc sine, A cosine. Come on, give me A cosine. So A cosine return the arc cosine or the inverse cosine of a number.
Yeah, okay, got it. Thank you.
So when you say like cosine minus 1, 0, he will tell you, well, it's 90. Cosine minus 1, 1, he will tell you it's 0. It's the angle. Good job. So alpha max, there is equation for it, right? There is also another equation that you see in the notes. That's the maximum alpha. It's 90 minus what? Minus L plus delta. And you can see how both of them are exactly the same. This is alpha at any hour. The equation for alpha, any hour, any day, any latitude, you get alpha. But alpha max specifically, which the hour angle is how much for alpha max? 0, solar noon. When you set the hour angle to be 0, the equation become cosine equals sine. Sine basically cosine L minus delta. And so if that is the case, then alpha, if the cosine of an angle equals the sine of the angle, that means that they share a 90-degree triangle with each other. And that's why it's 9 minus latitude plus delta. You don't need this, but it's nice, you know, to that they are agree. I always love to do this kind of like, when I'm doing a calculation, I like to do some kind of sanity check to make sure that I am really correct. Like I just give him something that I know the answer for. And I want to see it just to tell myself, yes, I didn't do any mistake in the conversion or the unit. Pn, right? And the E equation, and then the conversion to standard time, right? And then you pick them and you plot them. So I guess delta is like this, and you can see how E is doing, right? And the same thing for alpha max and what the day of the lens, maybe I think. So question about those angles. We have no problem plotting them, and doing in Excel is fine. Doing in MATLAB is even more professional and looks so cool. Okay, the only thing that when you do it in MATLAB, you have to publish the MATLAB file so that you have a PDF that show you here's the equation, here's the calculation. Okay, good, good, good. But, so we said last time the equation in the book for H limit was wrong, because in the book he said cosine minus 1, and then he said minus tan delta over tan L, and I said no, it's not divided by, and he also had the plus or minus wrong. So the correct equation is cosine omega s is cosine minus 1 minus tan delta multiplied by tan L. The tangential of delta multiplied by the tangential of the latitude. Okay, so this is going to be important in the project because that is the hour where the sun will show up. So before that time, you are all electric heater. And actually, even after that time, until the efficiency pick up, you are still going to run electric heater. Right? So let's see how he's going to calculate the efficiency. And after that, the key useful. Okay, so he need Tn, and so Tn is the ground water coming from the ground, the temperature. So remember in those last few days when the temperature was like freezing, one of my friends actually in Stillwater, his pipes were frozen. And he had to live in a hotel until the water come back. But he was not a mechanical engineer. Mechanical engineer don't have their pipe frozen, right? He's a biomedical engineer. So what do we do to make the pipe not frozen from us? We let it drip, right? You have to keep the water moving. You don't let it. So my kids, I was so proud of them. They were like, Dad, should we keep the water dripping? And I said, yes, let the water drip in all the. So amazing, like it was like minus whatever, but I mean, obviously the water was not frozen. Obviously the water is above 32. So the ground has its own temperature, right? And the deeper the pipe, the more it will be a little bit warmer, right? And so you guys will have to figure out what is the right temperature for the inlet water coming to your house for that project on March 1st in Tulsa, Oklahoma. Okay, here he said that water is coming at 58 degrees Fahrenheit. And then this is the temperature during the day, 25 at 8 a.m., noon, and 4 p.m. So what happened in the middle? I mean, you are lucky if you actually get like the minimum and maximum during the day or something. And then maybe you can assume the maximum at noon and you can assume the minimum at midnight or something. So what do you do in between? In this example, he basically made linear change between them. He basically said, if I started with this at 8 and I finish noon at this, I'm just gonna make it linearly changing between them. So if it's 25 at 8 and 45 at noon, so at 9 maybe it's 30, at 10 maybe it's 35, and at 11 it's 40, then at noon I'm 45, I'm fine. And you go the same way in the evening. Okay, so this is actually my solution using two different methods, two different equations, the linear eta and the second order eta. Okay, and you can see how, yes, the total BTU is a little bit different, 23,050, 23,337, but the kilowatt hour at the end of the day didn't show up because the number is like too small, difference is so small. So whether you are using the efficiency linear model or the efficiency second order model, you still calculated 6.8 kilowatt hour. But if you really look carefully, maybe this is like 6.75 and this one is 6.82. But at the end of the day, it's like 6.8. So that answered Denver question earlier, you know, like why do we use the linear model? Because it's not that horrible. So look at the temperatures. As the time go by, the T ambient, 25, 30, 35, 40, 45. And then you need to go back to what, 35 at 4 p.m. And so how can I go from 45 to 35? So you see the difference and you divide over the hour and like, okay, 43, 41, 38. So let's take it until we hit there. Okay, so we got T ambient, we got Tn constant throughout the day because the ground is not going to change its temperature from us, right? And this is the incident radiation on the collector because of his angle. Okay. So how do we get this from the normal radiation? If I have a table for the normal radiation, how can I calculate what's falling on me as a collector? What's the equation? Table, say normal radiation is, let's call it 500 BTU per square foot, BTU hour per square foot. How do I get those numbers then? I multiply by, not alpha, multiply by the normal radiation, get multiplied by what to find out the radiation exactly on the plate? Anyone? No. Free homework problem. What should I multiply the normal radiation with to find the radiation on the collector? Anyone online? I have the normal radiation from the table for this city, and I would like to find out what is the radiation on that collector sitting on my roof. What angle do I need to multiply with? Not the beta, not the alpha. What else do we have? What other angle do we have, guys?
Latitude.
What? I didn't hear that.
Latitude angle.
No, it's not latitude angle. Okay, what's next? What else is left for us?
Longitude.
Not the longitude, no. What else? Azimuth angle? No, not the azimuth angle, which is A, right? No, it's not. What else?
Delta.
Not delta. We are running out of option here. Come on, someone get a free homework problem. What else is left?
Alpha max.
No, not alpha max. What's left?
B.
Not beta. They already said beta. You're not listening. Instant angle. Free homework problem. What's your name? Okay, theta I. You need to send me an email today to remind me because I know that I'm gonna forget. So send me an email and said I had a free homework. Because 2 people so far has 2 free homework, and so you'll be the third. So we need to remember who did this. I'm just trying to charge the computer. Okay. Cosine theta I. Cosine theta I is what's standing between the incident radiation on the plate and the normal radiation. Okay, cosine theta I. Good. Okay, so that's how those things are coming from. Okay, that's how those things are coming from. So, and then you would use the eta equation, and once you have the eta equation, you multiply that eta by what? By this times the area. You will find Q useful. Eta by definition is Q useful divided by incident radiation times the area. Okay. So here is the temperature during the day. And here is saying, well, here is the table. And if you have a table that tells you exactly what is the latitude on your tilted plate, you are fine. But if all you got is the normal radiation, guys, look at me. If all you got is the normal radiation, this guy get multiplied by cosine theta I to get this. Okay, make sense? And we're gonna do it for March 21st for Tulsa. So we need a table for March 21st that tell us what is the normal radiation. And then we do it cosine theta I to figure out what would be the number that's falling in our roof, on our collector. So he got those numbers, okay? He got those numbers and he got them for every hour during the day. So here's the incident radiation every hour during the day. T inlet constant throughout the day and T emit is varying throughout the day. That's all he need, of course, with what? FR tau alpha and FR UL. So that's his equation. You will be able to calculate this efficiency. Questions? Of course, if you want to really be super accurate, you don't do FR tau alpha. You do FR K tau alpha. What's K? What's the K? Excellent. The incident angle modifier. Yes. Yes. And so Q useful would be that efficiency time I time AC. So now this area C, area collector, is it the box area or the aperture? What's the aperture? See, the box has a frame. Okay, the box has a frame and the glass part, the window part is smaller than the box, obviously, because the glass needs to be contained in the frame. So what is this area? Should it be the aperture or should it be the whole box on the top of my roof? To be right, to be fair to this guy, it's the aperture. But actually, no, we're gonna put the whole area. Why? Because the way they measure and document the efficiency, we need to measure it in the third-party tester, and they divide over an area to come up with this number. They divide Q useful over an area to come up with this efficiency, and they divide over the total area. Because again, to be fair, you are occupying that roof area. It's not our mistake that your frame is so thick, that your aperture is so small. That's not our problem. It's your design that made it with such a small aperture. Right? So it's the total area. So you can see here how he's calculating Q useful, area total, time I time efficiency, and you do it for every hour, and he add all those BTU. So those BTU that he collected, those are the one that you actually are harvesting. Those are, if you divide, this was in kilowatt hour, we multiply this by 10 cents, and this is how much dollar this collector has been collecting for you. This is the key useful that over the age of the project or that heater should accumulate to pay back the heater price and even more. Okay, that's what we collect, the BTU. Right? Questions? So this is interesting, this one. Find the percent of instant solar energy captured. So his Q useful that he has been adding every single hour. If he divide this over what has been falling during the day, he get that ratio. That ratio is kind of the daily efficiency. Out of all the radiation that we have been receiving, how much did we actually turn into hot water? Does this make sense? Q useful divided by the incident radiation during the day. Of course, you need to watch for the units. So that this is area time incident radiation to make it into. So the incident radiation is watt per meter square. You multiply by meter square, you get the watt. And you do it for every single hour, then become watt hour. and you have to divide joule over joule. Okay? Or kilowatt hour over kilowatt hour, or watt hour over watt hour. You have to make sure that this is the same unit exactly. Okay, so again, this was the daily, the hourly calculation. Every single hour, what's the efficiency? Because where is the sun and where is the radiation and how much is the ambient? So that's nice, but it's very exhausting computationally, right? So people rather do it just by months, okay? And so it's done by this method. This is called F chart. And it may look, especially when I show you this number, it may look really complicated. By this method is super easy. All its problem is how to read the x-axis and the y-axis. That's the only complication. If you really can figure out what's exactly this x and this y. By reading it, I mean you need to substitute in this formula. This is the x, this is the y. Okay, but once we figure out where we are in x and the y coordinates, what happened then? Say if x is 9 and y is 1, you come over here like this and you read which curve of those you are. What are those curves? f.1, f.2, 3, 4, 5, all the way to f.9. What is that f exactly? F is telling you what is the ratio of the monthly load by the solar over the monthly total load. This chart, basically based on analysis of many systems, can tell you in that weather, if the city is that cold and your load is this big, you should expect 50% of your load to be met by the sun. But the other 50% you have to run electric heater for. Okay? Or like 90.9% is going to come from the solar. Maybe in the summer, they will tell you, especially if you don't have that much load and the sun is really strong, maybe you will go up this high in the summer. Okay? So X and Y, one of them represent Q loss. The X is Q loss. So that tells you how cold the place is. Because if it's really cold, the losses will be crazy. Okay? And the Y, it's so this is always a ratio. Everything, all of them are divided by the monthly total load. Monthly total load, monthly total load. So each one of those guys, whether the F, which is how much you harvest with respect to the load, this is also how much you are losing with respect to the load, and this is how much you are absorbing with respect to the load. Okay? So if we just calculate the X and the Y, we can figure out how good the solar system is. So why it's hard to calculate X and Y? Units. The only difficulty is units. People always screw up this X and Y because the units are so confusing. Okay? So let's go through it and make it not confusing. So anytime you're using an empirical formula, not just in this course, any other course, you have to stick to the recipe. You cannot, if I say this temperature is in degrees C, you cannot say, well, why they are not in degree Fahrenheit? The chart was made for this, so you have to use exactly what they used to cook this to be able to use it. So 100 degree is the standard or the reference temperature, and T ambient is the T ambient in the city or the place that you are studying. Okay? So it has to be in degree C because the 100 was in degree C. So you have to put this in degree C, and then it will be the difference. The other important thing you need to realize too is that the top, the numerator and the denominator need to have the same units. Because this X is dimensionless and this Y is dimensionless. Okay, so when you say 10, that means the absorbed is 10 months, the loss is 10 times the monthly load. When you say 2, that means Q absorbed is twice the monthly load. Okay, so it has to be dimensionless. So if he gave us, sometime he gave us the load, that's the heating load, how much kilowatt hour or BTU or joules he need during that month for heating the water or heating the space. So he sometimes will give it to us in BTU. Sometimes he will give it to us in kilo hour. Sometime in joule. So whatever he gave, we need to make sure that the top, also the numerator, need to be in exactly the same unit. Okay. Area collector, that's meter square. And over here, I'm saying it's not just one collector, it's n time area of one collector, because this is a kind of this equation or this method you use when you're trying to figure out that HRC, how many solar collector we need to heat the space in the winter. We don't want to run electricity anymore. So it's not just one, it's like 20 or 40. Big building, basically, and you're trying to figure how many. So the number of collectors show up in that area. So if you're going to use 10 collector, it will be 10 times the area of one of them. Okay. As a matter of fact, a very famous problem in this chart is they will ask you how many collectors are needed, so that we can have 50% of the heating done by solar. And so then your target is that I want my F to be 50.5. So you calculate this guy, and so the Q absorbed like this, and you go to 50 and you read what is Q absorbed, and you say, it has to be 9. Then you come here, this has to be 9. Therefore, that N need to be 35 collectors. So I can make my X equal 9. Okay, so the chart can be used the other way. So rather than finding F, no, he can tell you, I want F to be this much. Find for me how many collectors are needed. Okay, so area C, total area of the collectors, FR prime, that's almost FR. What's FR? The factor we use to switch from T inlet to to switch from T average to T inlet. Remember, T average was more accurate, but it wasn't available for us, and we rather use T inlet because we know exactly what's the water inlet temperature is, because it's coming from the ground. So that was FR, and we said we will get FR from the equation of the collector. Well, here it's FR prime. People forget this. What's FR prime? We tell you it's 0.97 FR. Why? Because you are doing it for monthly calculation, and it's also based on experiments. You need to use the recipe. Part of the empirical formula. It's going to be 0.97 FR. UL, that is the collector overall heat transfer coefficient, and that is a mix up in the unit. So what unit is UL again? Overall heat transfer coefficient from heat transfer, watt per meter square Kelvin. So that watt is joule per second. If the load is in joule, then that delta T, which is the number of hours in the months, well, if it's watt, if UL is watt per meter square Kelvin, that delta T is not the number of hours, it's the number of seconds. So then the second cancel with the second, and this become joule, and this become joule, and this become dimensionless. If this load is in watt hour, this joule load is in watt hour, then that delta T need to work it out. That's all I'm saying. You need to work it out so that the time cancel with each other, basically. So actually, watt hour is joule. That's not the problem. You can turn this into joules. But here you need to make the delta T, the second cancel between this delta T and UL. Maybe what I wanted to say is that if the UL was given in BTU hour per feet square degree Fahrenheit, then that delta T need to be in hour, so that the hour cancel with hour. But the hour here in the load, that's piece of cake, because if it's kilowatt hour, you will turn it into joule. How you turn kilowatt hour into joule? 1 kilowatt hour is 1,000 watt hour, and 1 watt hour is 3,600 watt second, which is joule. So basically, kilowatt hour is 1,000 times 3,600 joule. Make sure, so right? Okay, so I just trying to tell you, make sure that UL delta T and L are dimensionless. Okay, the meter square will go away with the meter square, that area and that UL. So again, if that UL is given per feet square, then this area need to be in feet square. So it cancel with each other. You will get X, and once you get X, you will get Y. What's Y? How much is absorbed per monthly divided by the monthly load. So the absorbed is AC, FR prime. What's FR prime? Same thing, 0.97 FR. Tau alpha bar. What's tau alpha bar? Again, kind of corrected for the, because it's monthly average of tau alpha, and they basically say, let's just take 0.96 tau alpha. So whatever tau alpha from the collector, you hit it with 0.96. And whatever FR for the collector, you hit it with 0.97. You would think they should have done those already in the chart, make it built in, so that then you just go with your regular FR and tau alpha, and then all those numbers should be worked in the x-axis and y-axis. It wouldn't have cost them anything, right? Anyway, so FR, tau alpha, and this one, HTN. Okay, so HT is this is going to be confusing. Monthly average daily radiation. What does that mean exactly? Like what? Yes, it's the average daily radiation. So HT is the daily radiation. How much did fall on the day? But it's monthly average, not at the beginning of the month, not in the 10th day of the month, not in the 15th of the month, but what's the average for that month? Okay, and he's multiplying it by the number of day of the month. So then if this is how many watt per meter square per day, you multiply by the number of day, and that will be the total falling on the month, divided by the load of the month. Okay, so joule, cancel out. And so there are charts for liquid and there are charts for air. Like those collector don't have to heat water all the time. You can actually send air through them, get heated, and then back into your building. Okay, and you can use the chart or you can use the equation. So those charts are also can be used in the equation, and the equation is actually more accurate when you think about it. It's not that hard to use, and it's just function of x and y, as you can see. Okay, so here's an example. Like this example came maybe twice in my final exam. Calculate the thermal energy you expect to collect from a south-facing, that's alpha equal, sorry, A equal 0. Liquid-based collector, so I need to use the equation for the liquid solar heating, not the air, because it's liquid-based collector, tilted at 45 from the horizontal during March with a climate variable having the following value. Here is the temperature, T ambient, monthly average, daily insolation, 14 megajoule per meter square per day. Okay, latitude 38, heat exchanger solar collector parameter were as following. This is the FR prime UL 0.97 multiplied by UL watt per meter square Kelvin, and FR prime tau alpha bar, which is 0.93 times the 0.97 times 0.8, and area collector is this much, and the monthly load is this many joules. Okay, so you can see how he's calculating the X, and again look at the delta T, how it's being second, because UL was what? It was what? Joule per second. So I need to UL in joule per second, so I need to make sure delta T is in second. 31 times 24 times 6 times 60. Okay, and I calculated the X, and here is calculating the Y. And based on this, you calculate the F from the equation. F is 0.84. What does 0.84 mean? That load, that monthly load, you're going to meet 0.84 with the sun. So the energy collected will be this much. The rest is going to be used auxiliary. And we are done. Okay, there's be another example here. This is one example where you say, well, how many collectors are actually needed? How many collectors of those guys are needed to be able to hit 60% year long? All over the year, you want 60% to come from solar. And the load is done, the load is given for every month. So he will do this calculation for every month, get the F for every month, and then add all of them from solar, divide over the load, and say, did I hit 60%? No, not yet. Let's increase the number of collectors. Let's do it again. Did I get 60%? No, not yet. Let's increase the number of collectors. So this is a little bit more complicated because he has to do it for every month and he does not care. An easier version would be, I want every month to be 50%. That's easier than saying, I want the yearly load to be 50% or 60% by the solar. Right? So you have to do this in a MATLAB or Excel file. So he's doing it with MathCAD, basically. Okay? So the bottom line is that he will calculate the X, calculate the Y, same formula that we use, and calculate the F from the equation. Okay? And this is the number of collectors. He has 171. And he will change this number until what happened? Until the total collected divided by the total load is 0.6. And did you see this? What's happening? This is the F calculated for every month. In the summer, that equation will yield F more than 1. What does that mean? The collector is over-designed. The number of collectors is over-designed in the summer because he want to meet the load in the winter. So then he's like 1.5 or 1 whatever in the summer. Sun is high, load is not that high. We look at the load also. Load in the winter is 140, load in the summer 20. That's just like making hot tea and cleaning the dishes. No one is taking hot shower in the summer. But winter, a lot of heating, for example. So that F greater than 1 is, yes, the equation is leading more than 1, but in real life, no. You have to take it back down to 1. That extra heat will just sit in the hot tank. No one will use it. Right? So after you calculate the F from the equation, you say, that is nice, but no, we just have to stick to 1 when it gets that high. Okay? And so he keep repeating until he figure out what's exactly the number of collector that will get the total. Questions? So do you know everything you need to know now about solar collector? You know where is their chart, how to use their chart to calculate the load, their efficiency, and how much they can make. And you can even do it for the whole month. Right? Questions? All right, we are done. Thank you so much. Thank you.